Okay, maybe I'll start now. First of all, we assume we have a Riemann surface. We always assume that it's smooth and compact and has genus G. Gamma and G. Let me recall divisor. Divisor is a collection of points with integer multiplicities. We have a collection of points gamma 1, gamma k, and numbers n1 and k with some integers. D is okay. So we consider now divisors are such formal linear combinations. Of course, they form a Abel group. And of course, we assume that they are finite. Of course, n are non-zero. Or if n zero, we simply remove the point. Then, the important question, we have a function. Is it possible, we have a divisor. Is it possible to construct a function with prescribed restrictions? What are the restrictions? Roughly, usually write it is greater than or equal to 0. It means the following. Divisor, definition. 0 if all n j are positive. Of course, we assume that non-zero. We remove 0, and so divisor is called positive if all positive. Assume we have a function.
Gammas are points of the Riemann surface, right?
Yes, gammas points in the Riemann surface. Yes, points of the Riemann surface. One and k. Assume that we have a function. We tell the divisor of zeros of poles of meromorphic function.
If all strict and quality.
Okay, we can write, but we assume that nj are non-zero because we remove 0. Yes, if we have 0, we don't forgot about this point. We would like to have Abel group, and of course, so then we may assume that non-zero.
This one knows it. Yes.
Sorry.
Exists.
Of course, we have empty divisor. Unit in the Abel group is empty divisor. You agree?
Okay.
Yes, k can be equal to 0. Of course, we have empty divisor. Empty divisor is the unit of the Abel group. You agree? Empty divisor. No zeros at all.
Okay.
And we assume that n are non-zero, otherwise you understand. Because we would like to have Abel group. We have a point. You have d1 is, for example, to gamma 1. Then minus d1 is minus 2 gamma 1. You understand? So, of course, formula is 0 times gamma 1, but it's empty divisor. You don't count, we remove points if n equals to 0, so forth. Therefore, use the have function. It may have some zeros, some poles. If gamma k now is 0 of order k, so assume that okay, p1, ps zeros of f q1, qt poles of f. Then divisor d of f hello minus TQT, where n1 is the multiplicity of the 0, 1, p1, and s is the multiplicity of the 0, s. Order, n1 is the order of pole q1, and so at p1, you understand? Of course, at pj, j then all C and D are assumed to be non-zero. So, you have a function. Consider you have a meromorphic function. Consider a meromorphic function. Then denote the zeros of the function at p1, ps, denote the poles of the function about q1, qt. Consider expansion at h0 and h pole. This is order of the pole 0. This is order of the pole. Therefore, d of f is the following divisor. Understand? Moreover, definition: divisors of meromorphic functions are called principal divisors. Definition. Def principal divisors. By the way, maybe I don't want to use it immediately, but nevertheless, maybe let me recall also important definition. What's the Jacobian of curve? One is the possible definition. Well, no. Now, also another definition: degree of divisor. The sum of these numbers. The sum of these numbers is called degree of the divisor. Simple exercise: degree of a principal divisor is always 0. You agree? Degree of the principal divisor. It's a good exercise, but okay. Now, divisors of degree 0, one principal divisors. The factor of all divisors of degree 0 by principal divisors is called Jacobian variety. Maybe I don't want to go. Maybe at this moment I don't want to go into this direction, but nevertheless. Okay. But what's more important? Now, so is the definition. Consider L of L0 of D. Assume we have divisor. We call roughly equivalently, it means the following. So we have divisor D. If D has order, for example, point gamma 1 goes, what does it mean? What does it mean? Let's L0 of D. Is a space of meromorphic function with the following properties. If we have point gamma j, if nj greater than 0, then at no, it's the following definitions. First of all, a function f belongs to this definition. The function f gamma belongs to the space L0 of D if first holomorphic outside first of all, you have some divisor, D. We assume that function f belongs to our space, first constraint, outside the points gamma 1, gamma j, gamma k, the function is holomorphic. It may have zeros, but it has no poles outside the divisor points. And the second condition is at these points we have the following constraint. But of course, for example, if function, you understand that 1 you agree, it's valid. It's not greater than, you understand. So I mean this, it's inequality. This constraint is inequality. You can function may be regular, may have, if we have this constraint, it means function may be regular, may have first order pole, second order pole, and third order pole. But fourth order poles are forbidden. You understand? And also, if n is minus 2, for example, it means that it has at least second order 0, but it may have third order 0, fourth order 0, and so on. You understand? It's inequality. Therefore, such functions form a linear space. Let me repeat again, like polynomials of degree not greater than n. You understand? Because if you consider polynomials of degree n, they do not form a linear space. You understand? Because if you have polynomial z squared plus 1, they both have degree 2, but the sum has degree 1. So if you consider polynomials of degree 2, they do not form a linear space. But polynomials of degree not greater than n form a linear space. Understand? You have inequality, but not. Here we have the same, it's inequality. Now, for us, it's important to be able to calculate how many functions satisfying this condition we have. So, problem. So, let's do problem. Find zero of them. Of course, we will prove the answer will be given by Riemann-Roch theorem. And let me explain. Maybe I'll try to prove it, nevertheless. Let me try to prove Riemann-Roch theorem. First of all, how to construct such functions. Consider two spaces. One space will be let me introduce two principal spaces. First space will be L0 of D. L0 of D will be meromorphic divisors. Meromorphic differentials, sorry. Meromorphic differentials. Значит, first of all, no, I assumed, I'm sorry, I have to introduce. May I remove it? Remove it. I think let me write D Understand? We collect all gammas with positive and with negative. Okay, we can assume that we have such enumeration. So, I'm sorry. Consider such differentials, you understand.
Sorry. 1 plus.
Or 1.
Plus 1.
Plus 1. For example, differentials of first and second kind. So, first of all, we consider only meromorphic differentials with all residues equal to 0. You understand? Consider the space of meromorphic differentials with the following property. First of all residues are equal to 0. You agree? In second property, first, that if we consider only positive d plus, if n1 is equal to 1, it may have pole of order not greater than 2. You understand? So if we have gamma 2, if nk equals to 2, that the differential may have third order pole. You see this constraint. Let's calculate the dimension of this space. Of course, the dimension of this space is dim Yes. You agree? Oh, no, I'm sorry, sir. Yes. No. I'm sorry. No. Maybe I would consider a different space. I'm sorry. Sorry. I made a mistake. Let me correct it. L0 is meromorphic differential. Such that fast. I'm sorry. Sorry, I introduced wrong. I'm sorry, you understand. Let's do the differentials. First of all, they have, so what are the properties? The integrals of these differentials are 0 over all singular points and over all A cycles. You understand? And then we have this constraint. So, okay. Now, let me introduce another space. Sorry. First of all, this, for example, in L2 also, space are meromorphic differentials. But the difference is, in this space we have only differentials with these two constraints. L1 is bigger. No, not bigger, but different. L1, we have only one constraint. D minus, minus D minus. So,
Sorry. In definition, D minus
yes,
and L1 of
minus.
D minus D
Yes,
or D minus.
maybe I don't know, but okay. Minus D, because we take only, but I would like to stress, okay, may use this notation. In both cases, we use only positive part of this bracket. You see. So here you have positive part of D, you have positive part of minus D.
Okay.
So negative part of D. You understand? So you introduce here. example. You see that we have genus 2, for example. Example, for you have genus 2. You have minus such divisor. What is the space of okay. G if so if the minus is empty divisor, then we have no poles, therefore its degree is G. If it's not empty, it's G minus 1 plus, you see, they are all negative numbers. Why minus 1? Because you remember you have one constraint. The sum of residues equals to 0. You don't have divisors with one pole, remember. The sum of residues equals to 0 implies one constraint. In fact, it was proved at the previous lectures. This you recognize. What was not proved, but I refer to the theorem from the book by Springer. That first of all, we have G-dimensional space of holomorphic differentials. Then, for each singularity, with 0 residues, we can write a differential of the second kind with this constraint, and it's unique. So, in principle, we calculate is done. So it's the statement is a reformulation of the theorem from the Springer book. Because we can write arbitrary singularities with 0 residues, you understand? And if you put this constraint, then the differential is unique. So it's exactly the same statement. Understand it? Less different. In the second case, we have G-dimensional space of holomorphic differentials, plus we have meromorphic differentials. We have only one constraint meromorphic differential. The residue is equal, sum of residues is equal to 0. Remember. So this space contains differentials only of the second kind. Here you have differentials of first, second, and third kind. You understand? We have two spaces. Now, then, for example, what are the space in this case? 3 gamma 1 plus 2 gamma 2 minus gamma 3 minus 2 gamma 4. What are the spaces? Hertz spaces are L0. What is L0? It's formed differentials. One, 4. So what are the differentials? Omega 1k has the singularity of you remember, omega k has such differentials. Omega 2. So it's 5-dimensional. And what we have here? Genus equals 2, for example. What's the space L1? L1. First of all, we have differentials omega 1, omega 2. Yeah, you agree? Base of holomorphic differentials. Then we have differentials omega 1, 3, 4. It's differential set kind. It is now you have differentials omega 2, 4. Well, so understand. So in this case, what is dimension? 2 is 4, you see. Two differentials of the first kind, one differential second kind, one differential of the third kind. You see. Therefore, the G 1 plus 2, 3 minus 1. You see. Is it clear, the spaces? To understand these two spaces. Okay. Now we have the following bilinear. We have the following scalar product, skew symmetric, pairing on the space. You have this 4n1, 4n1, and we B2. One. You remember, we introduced this. And and integration over the boundary. You remember. And Riemann bilinear relation states that it can be equals to G AJ omega 2. So we have the following sum. It was theorem about Riemann bilinear relations. You remember? Remember it? You recognize this formula.
Yes.
So. But we have this scalar product. Now, assume that we would like to construct a function from L0 of D. What we know? First of all, it's evident that f the if. Let's write necessary and sufficient condition for the function to belong to the space L0 of D. Direct, not curled, but direct. If first. Yeah, you agree. First of all, I think it's evident. Function has zeros of poles. If function has pole of order k, then its differential has a pole of order k plus 1, you agree? You agree. Second, by definition, we have this constraint, you understand? But we have the following constraint. You agree? What are the constraints of the differential?
Sorry, df?
df. Okay, df. I'm sorry, df, of course. df. And the third constraint. If, okay, if and the third constraint is the following, we have two cases. No extra constraint, you understand? If and then okay. It means the following. Assume that f has zeros. You see. If it has it leads to zeros. Then we have the following constraint. Because it has two zeros for interval df. And the fourth constraint, then if some n j, we have j greater than n, if nj greater than 2, then minus nj, sorry. If some zeros have 0 to or greater, then we have one constraint df omega s omega s j equals 0. For example, assume that we have, assume that, for example, we assume that f has third order 0. You understand? Assume that it has third order 0. If f, for example, point gamma 3, something like this, then we have such expansion. What means that df, we have this scalar product, do you agree? It, sorry. It means that if you consider the following objects, C3, you see, okay, maybe res. And you have you agree we have these identities because this product is regular. Since f has third order pole, then this expression is regular. This expression is regular. Therefore, the residues are 0. Therefore, the integral is 0. You understand? It's necessary and sufficient. What is the condition that it has? What is the condition of the function that has third order pole? To have condition that the first of all, if it okay, let me do this. Okay. We have, for example, consider such expansion. Plus C2 plus so on. You have this condition. Of course, we see that you agree? because by definition, omega 2, 3 plus regular term.
Sorry, f is a polynomial of degree 3.
No, we have extra terms.
Oh.
It's expansion.
Function.
Meromorphic function, yes.
Okay.
So you see that you agree. What does it mean by definition? Omega 2, 3. The differential with the following singularity. Therefore, the residue equals to C1, you agree. You see.
One race?
Yes, one.
Okay.
The same. Sorry, is it clear? Are any questions? Because let me recall, what's the definition? Omega 3, 3 is the differential with only one pole at the point omega 3. What is the differential omega 3, 3? It's meromorphic differential with only one pole at the point 3, 3. And with singularity of third order. Only. This. Therefore, you see this, you have these constraints. Okay? So we have. And also, this is the following. And also, we have one integration constant, you agree? Have one integration constant. If f has no zeros, we can arbitrarily choose it. If it has zeros, we use it to kill 1 0, to make function 0 at 1 0. And at other zeros, it's 0 because of this. And in fact, this collection of constraints is necessary and sufficient, you agree? So we have differential. How to check if the differential function was prescribed properties? First of all, you have constraint on the poles of the differential. You agree? Then all b periods are equal to 0. All a periods are equal to 0 because the third property is that this, if you have more than one 0, then integral from one 0 to another equals to 0. And the final is this condition. You see. And these conditions are necessary and sufficient. Okay? Now, we use Riemann bilinear relations.
Could you repeat why the integral of the b period vanishes because of the...
No. It's a differential function. All integrals are equals to 0. You see. All integrals over a periods and over b periods. But first of all, it's differential from this space. You see. All differentials from this space, by definition, has 0 a integrals. So we have to put extra constraints b integrals are equal to 0. You see. That we have two g constraints on the periods. But first half of constraints satisfied by this property are included here. Included to this, you see. So we have to add the second half of constraints. You understand? You have two g constraints on periods. All a period integrals over a periods are equals to 0 because it's differential of a function. If you have differential of a function, all integrals are equal to 0. You agree? All integrals. But therefore, we said the differential belongs to the space, you understand. And so this condition is included to this point, you agree. It's hidden here. But we have remaining G conditions, and we have to write them explicitly. You see. You have two G constraints, but first half of the constraints are hidden here. Here you have only the second half of constraints. You see? Again, you would...
This theorem following Riemann-Roch?
No. We would like, no, what we know, we would like to construct a differential, a function.
Yes.
So, what we do, we, instead of function, consider differentials. What is good for differentials? You have existence theorem. It's not Riemann-Roch. You have existence theorem for differentials. So, we write a differential. But we have to check the differential is a differential of the function with the required properties. You agree? First property, all periods are equals to 0. Then you have this constraint, you have this constraint, you see. It's differential function. For a differential function, these two constraints are automatically fulfilled, you see. If you have a differential function, it has 0 residues, and it has 0 periods. Therefore, differential should belong to the space. You understand? First constraint. Then, it shall also be periods equal to 0. Therefore, if these two constraints are fulfilled, that we can take the primitive and we obtain a meromorphic function. You agree? So you have differentials, find these two constraints. Then its primitive has all periods equals to 0. Integrals over all poles equals to 0, and integral over all periods equals to 0. The primitive is single valued. These two conditions, this plus this means that the primitive of this primitive of the... If you assume that we have differential with these three constraints, with these constraints, this plus this plus this, omega satisfies these three constraints, then its primitive is single valued. Understand? Because you have meromorphic differential, and you write primitive of omega. Write primitive. We would like to have a function, a single-valued function. What is necessary and sufficient condition? Integral over all poles equals to 0. Otherwise, you have logarithmic singularities. You understand? So we have this constraint. You agree? Then, and integrals over all periods are equal to 0. What you have meromorphic differential. What's necessary and sufficient condition? That the meromorphic differential is a differential of some meromorphic function. Necessary and sufficient condition. Integrals about all poles equals to 0, and integrals over all periods are equal to 0. You agree? It's necessary and sufficient. Therefore, we have this constraint plus this constraint plus this constraint. They are necessary and sufficient. Next constraint, the poles have order not greater than, you understand? You have upper bound to the order. Upper bound to the order is here. We agree. If our function has second order pole, differential has at most third order pole, you agree? Is it clear? If you differentiate, we increase the order of pole by 1. So we have this constraint. Now, this But we also have constraint not only on poles, but only on zeros. First of all, we can always, by choosing a constant, fixed 1, 0. You understand? If d minus is empty, you don't have these two constraints, you agree. But assume that we have, first of all, at least, we always can, by choosing a constant, to make function 0 at one point, you agree. We have more than 1 point. Then we have this constraint, you agree. If you agree that we have constraint f if it vanishes at 2 points, it means that interval of df from 1 point to another equals to 0. You agree? We have these constraints, and we have. And now, if we would like to imply the function has high order zeros, in addition to these constraints, we have these constraints. Understand? It's clear. So it's full set of constraints. Okay. Now let us use Riemann bilinear relations. Using linear relations may not repeat the results of previous lecture. Remember? Integrals of periods of omega equals to, you remember it was identity, that's the scalar product. You see, because of course, we can use Q symmetry. We can have d omega, but you remember. Then, and the third constraint may be rewritten using the Riemann bilinear relation as remember, it was proved at the previous lecture. Remember? You recognize this formula? Sorry. You recognize. At the previous lecture, it was proved that this scalar product exactly equals yes, remember it was. Therefore, you proved this. Therefore, we came to the following conclusion. That we can now rewrite the necessary and sufficient condition. So is it clear what I'm doing? Sorry, you were at the previous lecture. You remember there were some bilinear relations. And we proved that. Remember, we proved this. Therefore, it means that everything can be written in the following form. Two conditions. First, df belongs to 0 of t, you agree. A second condition. Okay? Okay? So, in fact, we prove the following important lemma, key lemma, that necessary and sufficient condition is this one. Okay? Now, the second thing. Some sense is also easier. Introduce the second space, differentials. You remember, sorry, I'm sorry, L0, I'm sorry, of course. This is, sorry. Now we introduce second object. L1 of minus d, this. It will be meromorphic one forms of the first, second, third kind, here all of them, such that let's see. There is such space. So, if functions are permitted to have second-order poles, the forms here are obliged to have at least second-order zero. You understand? Opposite divisor. How to characterize these forms? First of all, okay, let's formulate a second lemma. If first constraint you agree. We permit at the points where f is obliged to have zeros, at the points from d minus, omega may have poles, not higher than. So this is the second constraint. And second constraint, where at what happens at the point d plus? Okay. At the point d plus, omega should have zeros. The second constraint is the same. You check that it's constrained on the poles. You agree? On the, because if differential has zero, it's the same residue condition. You see? It's a form. So, finally, we came to the following conclusion. I'm sorry, it's a little long consideration, but nevertheless, I think we prove the following. Okay, the principal lemma. You agree? Okay. So, in some sense, what we can do the following. And there is some basis of differentials here and here. The both spaces consist of differential. And let's introduce matrix. You agree? Of course. Now, very important moment. We do not know the rank of this matrix. You agree? The rank of this matrix is not known. But what we know, dim has rank A. You understand? This means the following. If we have no zeros, we can add an extra constant. You agree? If you have this 1, 0, it fixes the integration constant. So we have this form of identity.
Basic principle of lambda.
Okay, let me write dig. No, it follows from this. What is this? What is the necessary condition? This. You have this set of linear relations. So what is the space of solutions? The dimension of space minus the rank of matrix. You agree? Linear algebra. You have simple linear algebra. You agree? Simple linear algebra. The dimension of space, this space, is dimension of this space minus the number of relations, plus maybe one integration constant in this case. You understand? Linear algebra, nothing more. And we have this formula. Let me. Okay, we have this formula. Sorry, L1. I'm sorry. I made a mistake. Oh, I'm sorry. Sorry. Correct it, please. So, I'm sorry, correct it. Now, and we can calculate okay, may I remove this? You remember the middle part? Agree. You agree? A transposed, but it's the same. You understand? Okay, maybe, I don't know, I can write somewhere A transposed, but the rank of A and transpose is the same, so you understand it. Therefore, combined the following, we obtain theorem. What's important? We take the difference, the rank is subtracted. And now we have, it's called the Riemann-Roch theorem. You understand? Sorry, but I decided to explain it. I hope I explained it. You see. What was, okay, let me repeat. What was the main idea of proof? The main idea of proof was that first, we introduced these two spaces. Then we proved that how to characterize L0. It's, we take subspace of L0 satisfying these pairing relations. You agree? And we maybe add one if, in this case. And okay, we have the same pairing relations. We have two pairs of relations. You remember, we had these conditions. These conditions were necessary to obtain functions from A0. These conditions were necessary to obtain differentials. And therefore, you have the rank of the system is the same as the rank of the system. Okay? So we proved the Riemann-Roch theorem. Understand? Okay. And now now we can slightly change. Assume now that we have, instead of differential, instead of functions, we have minus k forms, minus L forms. So you have L0 of D will be forms of minus L from such objects. Consider now another pair of space. For example, vector fields and two forms, you understand, different tensors. But how to obtain any such tensor? How to construct such tensors? You need to have such tensors. you simply do the following. To construct such tensor, you multiply, you fix some omega 0, some one form. It's one form, any one form. It's not essential. Consider any one form, omega 0. Then we can do the following. Instead of consider elements P, instead of consider such forms, we can consider for F. Multiply all these elements of the space to this L's degree of this form omega. Agree.
So what is omega 0?
Any or to the degree L. Okay, we can, yes, if omega in local coordinates, such tensor.
What is dz?
The tensor. A tensor.
In
Normal symmetric tensor.
form. Symmetric.
Yes, it's not symmetric form. Tensors.
Okay.
Normal tensor.
Okay.
What is the difference? Denote by k zeros. Not by k is a divisor of zeros of this form. It has degree to g minus 2, if g is greater than 1. Yet it always has degree. It always has degree to g minus 2. Because it's my meromorphic form. In case g equals to 0, it's meromorphic form. Understand? That
Sorry. What is k? Is
k capital.
k capital?
Divisor of zeros.
Divisor.
Divisor of zeros. Divisor of zeros is the form omega 0. Therefore, the problem of constructing an element P with divisor D equivalent to construction function f is the problem of constructing element P is the same as construct a function with this divisor, you agree? how to construct some form, P, no, forms of some tensors P. We write that P is F. We simply write P, we use this definition. You see. But what are the, but with only one constraint, that it shall have extra zeros of degree L at the zeros of omega, you see. Therefore,
Okay, I understand.
you understand it?
Yes.
You simply. Therefore, we apply the Riemann-Roch theorem, but we have degree d tilde, you see. Apply. And the L1 will be these forms, and also will divide to the. You see. Therefore, so in this case, if you consider L minus L forms, and the conjugate spaces will be L plus 1 forms, we will have this version of the Riemann-Roch theorem. It follows simply from these relations. You'll have degree d tilde. Now, yes, my time is coming to the end, but okay, let me formulate the main corollary. First of all, you understand, so I proved the Riemann-Roch theorem. The main corollary, maybe the main example we required. First of all, you know what the space of vector fields. Consider vector fields L0 consider holomorphic. Consider holomorphic. Let example. Zero. N equals to 1. So L0 will be fields and full differentials. You understand? L is equal to 1. So elements of L0.
Sorry. L0.
Consider such pair of spaces.
We built vector fields. No?
Sorry.
L0,
L0,
sorry. L0 is
holomorphic vector fields.
subset holomorphic function.
No, holomorphic vector fields, a different story.
Sorry. Okay.
We consider L equals to 1. It was L equals to 0. We can consider L equal to 1 for arbitrary L.
Holomorphic vector space.
Fields.
Of fields. Vector Okay.
So for what do we have?
I think he means that L0 was some space of meromorphic function.
No, first of all was this version. Now we introduced another. L0 are the functions of this type, and L1 is the functions of this type. Extension of Riemann-Roch theorem. We added L, you see. Then we added L here. You see. Therefore, it's you can see from this formula. See.
There's Rimanoff.
Yes. But now, what's important? Assume that you know that if you have Riemann sphere, we have three generators of the Möbius group. Generators of the Möbius group are holomorphic vector fields. Therefore, this space has dimension 0. You understand? Relevant. And maybe your question is why we do not need, why it's important. Because we will prove that, in fact, the space is the space of is fact we will study the moduli spaces. So we'll calculate the dimension of the moduli space. How to calculate dimension of the moduli space? We will show that moduli space, elements of moduli space corresponds to the so-called Beltrame differentials, deformations. And this deformation is non-trivial if and only if the pairing with this space is non-trivial. Therefore, the space of moduli space has the same dimension as this space. We'll prove it in the next lecture. Therefore, to calculate the dimension of the moduli space, we have to know the dimension of the space. We need the dimension of the space to calculate the moduli space. Now, first of all, I will explain the following next, because the deformation of complex structure are described by Beltrame differential. But not every Beltrame differential generates non-trivial transformation. Transformation is non-trivial if the Beltrame differential is not orthogonal to all holomorphic two forms. Therefore, the space of the moduli space is the moduli space have the same dimension as the space. So we need the dimension of the space to write the answer. The dimension of the space is written, we calculated using the Rimanowy theorem.
Sorry, in case J1, dim L1, in case J1, no dimensions module space.
Yes, it's 1.
1,
Yes.
2.
No, complex 1.
This complex.
Yes, of course.
dimensions.
Of course, this all dimensions. Of course, I have forgot to tell that the dimensions are complex. When the real dimensions will be 2 and 6, j minus 6. They are complex dimensions. Okay, maybe it's a good remark. You understand? So all dimensions were complex in this approach. All calculations done today were about complex dimensions.
Yes.
All. Okay, maybe I would like to finish for today.